Welcome to the Ontario High School video podcast series. We are now going to talk about solution stoichiometry. We've talked about stoichiometry when we begin with the masses of certain reactants or products, and we've also talked about what we do when we have a volume of gas involved in a stoichiometric problem. So the logical progression here is to go to solutions, and I tried to give this a really fancy subtitle. You can see here molarity and functional stoichiometric processes. So, welcome. The entrance into solution stoichiometry begins with a concentration unit that we refer to as molarity. It's the most common concentration unit used in chemistry, and what it does is it refers to moles of solute, and solute is whatever substance you're dissolving, in 1 liter total of solution. Now, you learned earlier that a solution has two parts to it, the solute, which is what is dissolved, and the solvent, which is the dissolving medium. So for instance, if you have salt water, salt, sodium chloride, would be the solute and water would be the solvent. Together, the solute and solvent are the solution. And we're going to express this in moles per liter, or you'll see it also expressed as an uppercase M, capital M, and you'll see it both ways. Now, the most practical way to use it is in the moles per liter expression, and you'll see that as we work through problems together. When working with concentration in molarity, it is imperative. Now, imperative is a strong word, and it's deliberately chosen here. The solution is expressed in terms of volume in liters. So if you're given a volume in milliliters, you need to convert that using this relationship. 1 liter contains 1,000 milliliters. So let's look at how you determine the molarity, or the concentration in moles per liter. A typical problem involves being given the mass of the solute in grams and the volume in either liters or milliliters. For example, what is the molarity of 225 milliliters of a solution that contains 15 grams of KCl? Preliminary steps when we're doing molarity problems. One is to convert the volume from milliliters to liters. So we do that by multiplying our 225 milliliters by the equality or conversion factor of 1 liter on top and 1,000 milliliters on the bottom. When we do this, the milliliters will cancel and we're left with 0.225 liters. Another way of doing this in your head is simply to think about if you are given a volume in milliliters, move the decimal place 3 places to the left and you will change it to liters. Okay, 1,000 milliliters in a liter. Now, we want to set up the concentration units in what we're given in terms of grams per liter. So we put 15.0 grams of KCl over 0.225 liters, and that's our entrance into solving for molarity. Our final step, once we have our grams over liters or grams per liter, is we want to convert our grams of solute to moles of solute. So we multiply by that equality or conversion factor of 1 mole of KCl, the unit we're going to, will be on top, and the number of grams of KCl in 1 mole, which is 74.543 grams of KCl. Remember, that's just the molar mass is calculated from the periodic table. And when we do this, the grams of KCl will cancel. We'll be left with moles per liter as our unit, which is proper. So we take our 15 grams of KCl times 1 mole, and then we divide individually by 0.225 liters and by 74.543 grams. And when we do that, we get a molarity of 0.894 moles per liter of KCl. Remember, this can also be expressed as 0.894 with an uppercase M that represents moles per liter KCl. Want to give you the opportunity to solve for molar concentration or molarity of some solution. So here they are. For A, we'll have 20 grams of C12H22O11. That is sucrose, by the way, in 175 milliliters of solution. B will be 2.5 moles of sodium chloride in 4 liters of solution. And C will be 18 grams of HF, which is hydrogen fluoride dissolved in 0.725 liters of solution. If you will write these down and pause the podcast and go ahead and solve these, and when you resume, we'll look at the solutions. Remember the preliminaries. Make sure that your volumes are in liters, and that if you're given grams of solute, convert to moles. Welcome back. Let's check your solutions. For the 20 grams of sucrose in 175 milliliters of solution, change the milliliters to liters. So I have 20 grams of sucrose over 0.175 liters. I convert the grams of sucrose to moles by multiplying it by the conversion factor of 1 mole of sucrose over 342 grams of sucrose. And when we do that, we get 0.334 moles per liter sucrose. For our sodium chloride, this one was a very simple problem because your solute is already in moles and your volume is already in liters. So you just put the ratio, 2.5 moles of NaCl divided by 4 liters gives us 0.62 moles per liter of sodium chloride. How'd you do? Finally, the 18 grams of HF and 0.725 liters of solution. We put our grams over liters and then convert our grams of HF to moles of HF. So here's the solution. When we work this through, we get 1.24 moles per liter HF, and that was the final your turn problem. How'd you do? One of the things we want to get used to in chemistry can be very helpful if we can look at our concentration units as an equality. And in equality, we can use as a conversion factor when solving for either moles or for volume. So for example, I can write the 2 moles per liter NaCl as 2 different conversion factors. The first one being very conventional, 2 moles of NaCl per liter, or I can write it as 1 liter over 2 moles of NaCl. So we're going to do some problems where we're going to actually flip the molarity and have liters on top in order to solve for quantities that we're interested in, and that's where we're headed next. So continuing with our uses of molarity as a conversion factor, let's say we're given the volume of a solution and its molarity, its concentration in moles per liter. We can determine the moles of solute using the following relationship. Our volume in liters times the moles of solute per liter, which is the molarity. Our liters will cancel and we'll be left simply with moles of solute. This is going to become very important to us when we look at more complex solution stoichiometry problems. Here's a typical problem where using the molarity as a conversion factor can be real handy for us. We want to find out how many grams of potassium bromide, KBr, are needed to prepare 0.200 liters of a 1.85 mole per liter KBr solution. One of the things that we have talked about over and over again as we've approached stoichiometry is that in chemistry we cannot compare masses of reactants and products directly. We cannot compare volumes directly except under very special circumstances in terms of gases. Certainly not in terms of aqueous solutions. Volumes are much more complex than that. But we can compare moles, and in stoichiometry the goal is to get to the mole as fast as you can with the problem because it's the key to the solution. So here we're given a volume and a concentration, 0.2 liters and 1.85 moles per liter KBr, and we want to get to moles of KBr. Eventually we're going to need to get to grams, but we can't get there directly. We have to go through the mole as a unit. So the first conversion is to take my 0.2 liters, my volume in liters, times the concentration in moles per liter of 1.85 moles of KBr per 1 liter. When we do that, our liters cancel, and we're left with 0.370 moles of KBr. Once I have moles of KBr, as we have done dozens of times, if not hundreds of times, we're going to convert the moles of KBr to the desired quantity in grams. So our 0.370 moles of KBr times the molar mass of KBr, which we get from the periodic table, 118.99 grams of KBr over 1 mole of KBr, our moles cancel, and we're left with 44.0 grams of KBr. So if we want to prepare 0.2 liters of a 1.85 mole per liter KBr solution, we're going to dissolve 44 grams of KBr in enough water to bring the total volume to 0.200 liters. Let's look at a different kind of problem. Here we're given a mass of our solute, 25 grams of sodium chloride. We want to make a 3 mole per liter solution, and so we need to try and find what volume of the solution we would need to make with this 25 grams of NaCl for it to be 3 moles of NaCl per liter. So what we want to do first is change our grams of sodium chloride to the mole, because moles are very, very important in stoichiometry. It's where we need to go. So 25 grams of sodium chloride times 1 mole of sodium chloride over 58.453 grams of sodium chloride will get us 0.428 moles of sodium chloride. Now, I have my molarity. It's 3 moles per liter, and I have my moles of NaCl. So what I want to do is find the volume that I need to make in order to ensure that this is 3 moles per liter. So I'm going to take my moles of NaCl, 0.428 moles, times the molarity here flipped upside down so that I have 1 liter on top over 3 moles of sodium chloride. Again, the unit I'm going to is on top. So 0.428 moles of sodium chloride times 1 liter divided by 3 moles of sodium chloride gives us 0.143 liters total for the solution. So I would need to dissolve 25 grams of sodium chloride in enough water to bring the total volume of the solution to 0.143 liters. What I'd like you to do now is to write these problems down, pause the podcast, work these out, and when you're ready to see the solutions, resume the podcast, and this will give us an idea of how you're doing with this. So go ahead and pause the podcast, and when you're ready to check solutions, resume. Let's take a look at the solution to part A, in which we want to find the number of grams of potassium iodide, Ki, required to prepare 0.5 liters of a 1.8 mole per liter potassium iodide solution. So to get the moles of Ki, we take our volume in liters times the molarity, so 0.5 liters times 1.8 moles over 1 liter, and we get 0.900 moles of Ki. Once we have the moles of Ki, we can then convert to grams. So 0.900 moles of Ki times 165.99 grams of Ki per mole of Ki gives us 149 grams of potassium iodide. So we would need to dissolve 149 grams of potassium iodide in 0.5 liters of solution in order to get a 1.80 mole per liter solution. How'd you do? Let's look at part B. Here we're asking what would the volume of a 0.5 mole per liter Ki solution be if it is prepared with 122 grams of potassium iodide. So we first want to change our grams of potassium iodide to moles. So 122 grams of Ki times 1 mole of Ki over the molar mass, which is 165.99 grams of Ki. That gives us 0.735 moles of potassium iodide. Once we have the number of moles, we can then multiply by the molarity, flipped upside down so that volume is on top, because that's the unit we want to go to. So we have 0.735 moles of potassium iodide times 1 liter over 0.5 moles of potassium iodide. This gives us a volume of 1.47 liters. So in order to prepare 0.5 mole per liter solution of Ki, when we have 122 grams of Ki available, we would dissolve it in enough water to bring the total volume of the solution to 1.47 liters. How'd you do? As you get more experienced with stoichiometry problems, one of the things that you'll find is that we can combine our parts of the problems into one expression, and that's what this slide will show you. Is rather than separating out the conversions that we did, we just combine them into one longer expression. You get the same answer. And so if you want to look at this a little more closely, just pause the podcast and write these down and compare them to what we did in the previous solutions. Both are acceptable. Well, we've come to the end of part 1 of our Solution Stoichiometry video podcast series. I want to leave you with a quote by the author Lawrence J. Peter. A man doesn't know what he knows until he knows what he doesn't know. Chew on that one for a while, and stay tuned for part 2.